Okay, we're looking at how to use Hess's law today. And we're going to use two questions from Brown and others, 10th edition, question numbers 576 and 577. In the first question, our target reaction is to synthesize B2H6 from its elements, so boron and hydrogen. Notice that you need 3 diatomic hydrogen atoms, hydrogen molecules, and 2 borons to make B2H6 in the gaseous form. We have 3 reactions to work with. So the first thing we're going to do is look at the boron. The only reaction that has boron, elemental boron, is the first one, but it has 4 boron atoms, whereas we need 2. So we're going to take that first reaction and multiply it by 1/2. So it's going to have all the quantities. That's we're going to recopy it with half the quantities, and then we're also going to multiply the enthalpy of the reaction by 1/2. The second step is to look for hydrogen. We need 3 hydrogens, and we have 2 hydrogens. So how are we going to get the 3 hydrogens we need? We're going to multiply the whole reaction by 3/2. So if you multiply 2 by 3/2, you get 3. And of course, you multiply everything else in the reaction by 3/2. You also multiply the enthalpy by 3/2. That gives you the requisite 3 hydrogens. In the third reaction, we need to get B2H6 on the right-hand side. So what we're going to do is flip this reaction to put B2H6 on the other side. And then that's going to cause us to take the opposite sign for the enthalpy. So the enthalpy becomes positive 2147.5. Once we've done that, we eliminate everything that appears on either side of the reaction arrow. So we see that there's 3 water molecules on the left, so those are going to be canceled with the 3 water molecules on the right. These 3 oxygen atoms, 3 oxygen molecules, are going to be canceled with the 3 oxygen molecules over there. And what's left is the B2O3, which is also going to cancel. The 3 things that are left are the 2 boron atoms, the 3 hydrogens, and the B2H6, which we then write down as the target equation. And the math for that adds up to 35.4 kilojoules. So that's the heat of reaction for this chemical equation. On the next problem, we're asked to balance the equation for the combustion of octane, which we did over here. So we have octane combining with oxygen to give CO2 and water. And so we have 8 carbon dioxides and to give us the 8 carbons. We have 9 waters to give us the 18 hydrogens. And then to balance the oxygens, we're going to put 25/2 oxygens. The second part is to generate the target reaction, which is to form octane from 8 carbon atoms and 9 hydrogen atoms. So whenever we look up a heat of formation, like you have it on the appendix, which gives you the heats of formation of several chemical substances, it's the handout I'm going to give you here. So here I made a photocopy of all the heats of formation. So this is our target reaction. So we have to generate this molecule from its elements in their standard states. The first step in solving this problem is to flip the first reaction, which is the combustion of octane. So I've simply written this reaction backwards, and that causes, to do that, I also have to put the opposite sign on the enthalpy of the reaction. Then, because there's 8 CO2s and 9 H2Os, I have to get rid of those because we want it to be heat of formation for an element, for a substance, from the elements in their standard state. So in the case of octane, our target reaction is to form octane from 8 carbon atoms and 9 hydrogen molecules. So we're going to look up the heats of formation for CO2 and H2O. Notice how I put 8 CO2s so that I can cancel the 8 CO2s over here. And why did I put 9 heats of formation for water? Because I want to cancel the 9 waters over there. Then what else can cancel? The 25/2 oxygens is the same as 12.5 oxygens. Well, we have 8 over here and 4.5 over here. So 8 plus 4.5 gives us the 12 oxygens. So 12 oxygens on the left cancel with 12 oxygens on the right. Everything that's left constitutes our target reaction. The 8 carbons, the 9 H2s, and the octane give us a target reaction. When we add the math of all the heats of formation, we get negative 255.2 kilojoules.